Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome students. In the previous lecture we have discussed first order systems and its time response specification, and in this lecture we will discuss that how these time specifications will help us to identify the transfer function of an unknown system, and also after that we will cover the introduction of second order system. So consider that we have any physical system and we do not have its transfer function. So if we want to find out its transfer function, it is not possible for us to obtain it analytically because the system is closed and its component parts are not easily accessible or identifiable. But we know that the transfer function is the ratio of output and input in S domain. And if we know the input and the output of the system, we can find out its transfer function even though we do not know its inner construction. Now consider a simple first order system. So I can write its transfer function as K upon S plus A, and its step response will be C of S K upon S plus A. So step, here we apply step input. So if we want to find out its output response, then we have to perform the partial fraction technique. I am multiplying this equation both sides by the denominator term. S plus A. So we will get A of S plus A and B of S, and to find the value of these constants A and B, I am saying it equation 1. I am putting first S plus A is equal to 0, so S equal to minus A in this case, so K is equal to, this term becomes 0 and here it is minus A. So the value of B, constant B, will be minus of K upon A. And to find the value of constant A, we have to put S is equal to 0, and in that case the equation 1 becomes here it is 0 plus a, and b of this term becomes 0, and so finally the value of a will be a is equal to k upon a. So I'm placing the values in this equation. I'm saying it equation A. So the output response will be k upon a of upon s plus minus of k upon a of upon s plus of a. So this is the output response of the system for unit step input, and from this output response it is clear that there are only two unknown parameters, that are k and a, and if we can identify their values by the laboratory testing or by any other means, we can obtain the transfer function of this system. So for example, assume that we have a unit step response as shown in this figure, and it is clear that the form or shape of this graph have the same characteristic as of first order system. So we can assume it as a first order system, and if it is a first order system, then its transfer function will be k upon s plus a. To obtain the value of this transfer function, we have to find out the values of these constants k and a. Now in this output response, the final steady state value is around 0.72, and we know that the time constant is the time required by the output response to reach to 63% of its final steady state value. Here the final value is 0.72, and if we calculate its 63%, so it will be multiplied by 0.63, and the answer is 0.45. So now we have to calculate the time when our output is 0.45. So here I have drawn two straight lines, this one and this one, to find out the time when the value of output is 0.45. So here the time is around this time is around 0.13 second. So this is our time constant, and the time constant is basically 1 upon a, since we have to calculate the value of this constant a, here a is equal to 7.7. So by these steps we find out the value of this constant a, and now we have to calculate the value of k, and for that I am using the step response that we have derived earlier here, and here if I take inverse Laplace transform, so our output in the time domain will be k over a minus of k over a e की power minus at u of t. So this is the output response in time domain, and we know that this part of our output is basically our forced response, and this part is the transient response. We can say that this value k upon a, which is our force response, is our final steady state value, because as time increases, this value which is exponential term will become 0. So I can write it as k upon a equals to 0.72, because in this step response our final value is 0.72. So here we have to find the value of k. So I am cross multiplying a and putting its value, which is 7.7, and by multiplying these two terms we will get the value of k as 5.54. So now we have found the values of the constants k and a, and now the transfer function will become (5.54) divided by s plus 7.7. So in this way we have find the transfer function of an unknown system with the help of the time response specification. At this example, our first order system topic is completed, and now onwards we will discuss the second order systems. The second order system have two poles in the denominator. It means that there is a quadratic equation in the denominator of the transfer function of second order systems. In first order systems, we have an unknown parameter A, and by changing its value, we can only change the speed of the response, output response. But in second order system, we have a wide range of response, and by changing the value of the parameters of second order system, we can change the speed as well as the form of the system. To become familiar with the wide range of responses of second order system, we will solve some examples. Consider a general case of a second order system with 2 poles and no zeros. P upon s square plus of a of s plus of b. This is a general second order system transfer function. This is the input r of s, and this is our output c of s. Here the term b in the numerator is simply a scale, or we can say that it is a input multiplying factor that can take on any value without affecting the form of the output response. It only affect on the amplitude of the component parts of the output response. So there are 2 unknown parameters, that are this A and this B, and by assigning appropriate values to these parameters, we can develop all possible second order transient response. Since there are 2 poles or roots in the denominator here, since it is a quadratic equation, there can be 4 possible combinations of the roots. The roots may be number 1 real and distinct, or they may be complex in nature, or they may be imaginary in nature, and the last one, they may be real and repeated. So these may be 4 possible combinations of the roots, and I am giving them some other names. I am saying that if we have real and distinct roots, so we get overdamped response. And if we have complex roots, so we will get underdamped response. and if we have imaginary roots, so our output response will be undamped. And if we have real and repeated roots, we have critically damped response. Critically damped response. So these are the names of the response which will form with the help of these roots. Why we gave these names to these roots, we will discuss it later. Since there are 4 different combination of roots, each combination will develop a different form of transient response. So now first we consider the case of overdamped system. So for overdamped system, the transfer function will be s square plus of 9s and plus of 9. I am selecting the value of a and b both as 9 because it will give me real and distinct roots. So here output c of s, and here we apply the input. This is our transfer function. So I can write it, the output response will be equal to the input r of s multiplied by the transfer function g of s. So if we apply here the unit step input, then the output response will become 9 over s square plus of 9s plus of 9. And if we factorize it, then we will get the factor as s plus 7.854 and s plus 1.146. So these will be the factor. So if we want the output response, then we have to perform the partial fraction. So if here I develop the partial fraction terms, so the first term is a upon s, the second term will be s plus b upon s plus 7.854, and the third term will be s plus 1.146. So I am saying it as equation 1. Now to get the values of these constant a, b and c, I am multiplying these both sides by the denominator term, which is s plus 7.854 and s plus 1.146. So we get 9 equals a of s plus 1.854, S plus of 1.146, and here B will have S and S plus 1.146, and C have S and S plus 7.854. This is our equation 2. So to get the value of A, I am putting S is equal to 0 in equation 2. So equation 2 will become 9 is equal to A of, because this S is 0, so I will get 7.854 only, and also here S will be 0, so this will become 1.146, and by rest of the two terms will become 0. So from here we get, by multiplying these two terms, I get 9 term, and the value of A is 1. And to find the value of B, I am putting S is equal to minus or S plus 7.854 is equal to 0, or we can say S is equal to minus 7.854. So equation 2 will become 9 equals, this A term becomes 0, and in this B term, in place of S, I am writing 7.854, and here also 7.854 plus of 1.146, and the last term is also 0. So here, by multiplying these terms, we get 52.68, and the value of B will be 0.17. And in the last, to find the value of C, here I put S plus 1.146 equals to 0. So this makes the value of S to minus 1.146. So now the equation 2 becomes 9 equals, the first two term becomes 0, and the last term will have C multiplied by minus 1.146 and S minus 1.146. Sorry, minus 1.146 plus of 7.854. So now by multiplying these terms, we get minus of 7.687, and finally the value of C will be minus of 1.17. So the output response will be C of S equals the value of A is 1, so it will 1 upon S, and the value of B is 0.17 S plus of 7.854, and the value of C is minus 1.17. S plus 1.146. So if I take here inverse Laplace transform, inverse Laplace transform, so the output response will be C of t equal to 1 plus of 0.17 e की power minus 7.854 t minus of 1.17 e की power minus 1.146 t. So this is the final output response in time domain, and this part of the output response is the forced response, and this part is basically the transient response part. So the term 9 in the numerator here is responsible for the amplitudes of these two responses, the terms 1, the term 0.17, and the term 1.17, and it does not put any effect on the exponential term power, and this exponential term specifically, this and this, are basically responsible for the form of the output response. So that's why earlier we have said that the constant term of the numerator is basically a scaling factor and not put any effect on the form of the output. So again here, if we talk about the poles, so the input pole at the origin is responsible for the force response here, and the two poles of the system produces this transient response, and its exponential frequency, which is minus 7.854 and minus 1.146, is equal to the pole location. We can see it in the picture here that the values of poles are minus 7.854 and minus 1.146. So the value of poles is basically responsible for the power of these exponential terms. So now if we consider this diagram, so this is our overdamped response, and this is its pole plot. We gave it name overdamped because overdamped refer to a large amount of energy absorption in the system, which inhibits the transient response from overshooting and oscillating about the steady state value. So if there are overshoots in this response, then it will be look like this, and these are the oscillations. So here in this response there are no overshoots and no oscillations. So as the energy absorption capability of the system is reduced, an overdamped system will become underdamped and will exhibit overshoots. In the overdamped system, the damping is high, and it is clear from its name that it is overdamped. So due to high damping, the output response will take more time to achieve the final steady state value. So we will discuss the remaining three responses, namely underdamped, undamped and critically damped, in the next lecture.